So, welcome back. We are basically discussing several problem based approaches of a given target molecules, and we talked that transformation based approaches, starting material based approaches and functional group based approaches are the key core three strategies which can be combined together efficiently to solve numerous problems as discussed in the earlier lectures. Now, in continuation with the same thing, we will now try to provide you a problem which is similar, but you need to uh, figure it out the target structure in very closely. So, the 6 member ring is there, and in addition you have a 7 member ring. Then I am trying to draw 1, 2, 3, 4. So, this is the target molecule. Just try to draw the target molecule, and then this target molecule is bit complex. You have a bridge structure from here. Now, in reality the structure which was given here, it is a not a simple structure as it looked. The 6 member ring, then you have a 7 member ring 1, 2, 3, 4, 5, 6, 7. Then you are basically having a 5 member bridged 1, 2, 3, 4, 5. So, there are cyclic structures connected in a different way, probably a topological distinct molecule, but eventually we will be just trying to analyze the molecule in a very straightforward retro by normal functional group based approaches. Let us first do the very conventional retro, and then you will realize that how these retros are so powerful, so powerful. The only thing, if you check the molecule, you will find that a probably a aldol kind of transformation is useful to make this target molecule. Now, how? I will try to draw the structure. So, this is OBN, BN is benzyl, I am writing it, BN is basically benzyl, CH2 PH, it is abbreviated form. Then from this part you can fuse, or you can hanging, you can make a hanging aldehyde appendages. Okay. Then these things you can put something like this, and then you try to make the bridge, try to make the bridge. Now, we say that we are doing a disconnection here. Now, this is a methylene compound adjacent to a carbonyl, okay, and a close proximity you have a carbonyl or aldehyde group. So, basically it is a aldol reaction, it is a aldol transformation. Now, the structural simplicity is basically until unless you draw the aldol retro, it is not visible. That is why sometimes you try to make a visible or visual communication with this target molecule, and then try to simplify the main target structure. Now, this structure we will write it in a simplified form. If you write it, now you see the structure is basically nothing but a 6 molecule fused together isn't it? See the analogy. this is the O-methoxy, this is the fused, common fused together 1, 2, 3, 4, 5, 6. So, the ketone, this red colored ketone is basically this, and then you are doing it a aldol reaction with this aldehyde to this. So, this is the aldol reaction we are doing. Now, this compound has been rewritten in this way. So, that is what the structure looks pretty complex. Now, once is simplified, now you are quite comfortable. Now, it looks quite comfortable, and then probably you can design a very straightforward retro based on a known starting material. This starting material is known, is a 1, 2, 3, 4, 5, 6, 7, 7-methoxy beta tetralone. That was already known, and probably this is a beta tetralone derivative. It is a commercially also available beta tetralone derivative. It could be served as a very good starting material. Now, what exactly you want to do it? You will be doing a successive round of alkylation to put these functional groups. Now, remember, you are having a methylene groups here as well as here, fine. Now, out of this methylene group, this methylene group is most acidic because it is a benzylic also. So, that gives you a thing. So, you now you realize that if you start with this compound, again we will draw the parent compound, and you both the hydrogens you will basically replaced by some carbon containing electrophile, that will be given you the this target will then undergo intramolecular aldol reaction to give you the final target, is not it. So, let us start the forward synthesis. The 7-methoxy, the tetralone derivative which you choose. I said doing the successive round of alkylation. So, LDA 1 equivalent. Now, what are the groups need to be introduced? The first one is benzyl O, BNO, CH2, Cl. This is called benzyl oxymethyl chloride or abbreviated as BOM chloride, BOM chloride. So, first round of alkylation we get OBN. The second group which you need to introduce must have a CH2CHO. In principle, you can basically use this kind of chloroacetaldehyde. It is possible, definitely possible, but sometimes this reagent might not be easily available, So, what you do? You can try to take another source or another electrophile which will give you this particular functional group. So, alternatively, we will be using this reagent condition, we will be using LDA and allyl bromide. Allyl bromide is very cheap material, cheap starting material, and then you will basically do another round of alkylation to get this all carbon quaternary centers here, fine. Then as the situation demands, you need to do a oxidative cleavage here to remove this one of this carbon to get a aldehyde. So, do a ozonolysis. your O-methoxy group will be always there. You do a ozonolysis and then you basically getting this compound. Now, this compound you can now try to go back to the original retro. It is nothing but this. You try to draw it in this way and then do a intramolecular aldol. You can now finish it off the retro in a elegant way. So, that was basically very useful simplification. So, once you have a complex structure, that is why I always saying that the retrosynthetic pathways are so powerful. So, you have to start communicating with the molecule in a visual way, and once you try to finish the chemical logic, then you simplify the starting material or the intermediate, and then you complete the forward synthesis. As a very pleasing exercise. And next we will be basically trying to use a similar kind of strategy. We will be using a multiple transformation based strategies. They said sometimes transformation which you require is to be combined, couple of transformations like 3-4 transformation should be combined together, but till now we have not discussed any complex structures. So, basically simple structures where you can just play with 2-3 functional groups or 2-3 transformation. This particular target, which is now next we will be discussing, we will be using 2-3 transformations together, and I am sure all the transformations have been known to you or earlier discussed. This is a target molecule which contains a phenyl ring, and here it is having a appendage which is having a cyano, CH2OH and a isopropyl group. So, this carbon is a quaternary carbon with all carbon quaternary, the phenyl, cyano, CH2OH. So, I will do a functional group addition or a functional group interconversion, is purely FG based approach. Now, try to do, we will initially if we found somewhere the alcohol is given in the target molecule, means that the alcohol need to be protected. Normally alcohol protection we have not discussed, but we will do it little bit later on, but alcohol is not a good functional group which you can keep it as a free, because acidic hydrogen plays some important role. So, alcohol free is always not recommended, you can just protect it, a suitable protecting group. PG stands for protecting group. We will be talking about many protecting groups little bit later on when you talk about functional group based strategies in detail, protection group, fine. The next you will try to figure it out other FGI based approach, and then we said that this compound can be potentially created from a oxime which can give you a cyanide. Now, oximes are basically having this compound is the aldoxime, means aldehyde oxime. Now, aldoxime if you treat with a dehydrating agent, mainly phosphorus pentoxide, this water will be eliminating and you get the nitrile compound. So, what is this? This is basically a functional group interconversion, fine. Now, aldoxime means you need to have a aldehyde, otherwise you will not get aldoxime. So, this is again a FGA or FGI to come back to the parent aldehyde. CHO, this isopropyl remains similar and this group is protected as is suitable protecting group. So, we are here. Okay. Now, this carbon is all carbon quaternary carbon. The next retro was again based on a very conventional reaction which we discussed many times in our coursework. We said a Menold kind of rearrangement will give you this aldehyde. So, it is a Menold based rearrangement was used as a main transformation, Menold transformation. Now, you know the mechanism of Menold rearrangement, and you can, I am sure you can basically figure it out how this transformation takes place. So, next you need to make this epoxide, simple job. You can now make this alcohol free, and then if you have this kind of compound, this kind of allylic alcohol, you can easily make it. So, this is a FGI. So, the Menold transformation, as we discussed earlier, you know the mechanism, you can easily formulate. So, now this primary hydroxy group we are putting in a different way, we will be accessing this primary hydroxy group through a cyano group. Some of the reactions we are not discussing, but we will discuss it when we talk about forward pathway, and then this cyano will be discussing from a benzyl cyano through a intramolecular aldol reaction. So, all are FGI based on couple of interesting transformation. So, now let us go back to forward pathway. So, your forward pathway starts from a very simple starting material, benzyl cyanide. Okay. And this compound is subjected to first LDA. It is acidic compound, these hydrogens are definitely acidic. Okay. And then you react this compound with this aldehyde. So, aldol reaction will take place, and we definitely get these things. Okay. So, obvious, but now you go back to the retro, you will find this cyanide now needs to convert it to the corresponding aldehyde. You can basically do two different kind of transformations. Probably you know Stephen's reaction. Stephen reaction is a very simple reaction in which you can convert a cyano to a aldehyde RCN to RCHO by SnCl2. Otherwise, if you do not like the Stephen reaction, you can simply using a dibal, diisobutyl aluminum hydride, that will also selectively convert a cyano to the corresponding aldehyde. The beauty is the reaction will definitely stop in the aldehyde step. Usually it, if you use one equivalent of dibal, it usually stops at this aldehyde step. Otherwise, you can use excess dibal to get the primary alcohol, because in our synthetic experiences, synthetic exercises, we need the primary alcohols. Nevertheless, dibal is very expensive. So, what you do? You put a dibal one equivalent to get the aldehyde, then you use a cheap reagent sodium borohydride to access this allylic alcohols. Okay. Then this allylic alcohols need to be protected. The protecting group, normally you can use any protecting group, but I am giving you a protecting group whose name is TBDPSCl. The structure of TBDPSCl is tertiary butyl diphenyl silyl chloride. So, basically the oxygen will be replaced by this silyl ether, and you will be having this OTBDPS. So, this is your these things. You can do MCPBA mediated epoxidation here to get the corresponding epoxide, which will be next subjected to Meinwald rearrangement. So, now we are having this epoxide and this O, let us say PG, OPG. Meinwald rearrangement, they say normally you treat with a Lewis acid, it is Lewis acid. Okay. So, the Lewis acid you add and obviously make sure which way the carbon oxygen bond will be broken down. The most stable carbonium ion will be definitely generated, and I presume that this way you will be having this O L A things, okay, because this is a benzylic thing. Now, out of this there is a hydrogen, there is isopropyl. Isopropyl group is secondary, it will basically migrate. Isopropyl group will migrate here, and then once isopropyl group will migrate, let the isopropyl group migrate, and then you will basically get the all carbon quaternary center. This isopropyl group will definitely migrate, and you are having this CHO after this rearrangement takes place, which is basically nothing. The compound which is said is a put the isopropyl group in the top, this OPG and your aldehyde. Now, make this aldehyde oxime, aldoxime by hydroxyl amine treatment, the very standard FGI. So, what you will get? You get this OPG, OPG remains similar, your isopropyl group remains similar, and then you get the corresponding oxime. Okay. Put a dehydrating agent, maybe P2O5 phosphorus pentoxide, and you will get this OPG cyano here and your isopropyl. So, now we are almost close, only thing is you need to remove the PG. Now, this PG removal, this is basically oxygen silicon bond. We will try to give some more information. Now, this oxygen silicon bond is very labile under a fluoride condition, because you are going to form a new silicon fluorine bond. So, this will come here, you put a RO minus and it will give you the silicon fluorine bond. Silicon has a strong tendency, or silicon is very much fluorophile, the silicon fluorine bond energy is very high. That is why normally if you have a oxygen silicon bond or carbon silicon bond, the best way to cleave is treatment of fluoride source. Fluoride source here will be giving fluoride source, and then basically you can access the target molecules which is required. You will get a OH here, you get a cyano, the target molecule. Now, coming to the fluoride source, what kind of fluoride source you can think of using for silicon deprotection? Fluoride source, the best fluoride source what we will be using is named as TBAF, tetrabutyl ammonium fluoride. So, structure is NBu4 N plus F minus. Normally, all silicon containing protecting group has been clipped in this way, say ROTBS. TBS stands for tertiary butyl dimethyl silyl, which is equivalent to silicon, methyl, methyl this group. Okay. TBDPS, which we just now talked, which are commonly used silicon reagent, silicon protecting group. RO TIPS, TIPS stands for silicon triisopropyl silyl. There are other silicon containing protecting groups like RO TACE. TACE is triethyl silyl, means silicon, ethyl, ethyl, ethyl. So, all these silicon containing protecting group can be cleaved with tetrabutyl ammonium fluoride. This tetrabutyl ammonium fluoride basically was commercially available in THF solution. So, when you try to buy it out from commercial suppliers, you will find that TBAF in THF solution, tetrahydrofuran solution. So, normally 1 molar or 2 molar solution is commercially available, and you can just use them. In some cases you can use HF. HF was very strong acidic, and to minimize its acidic nature sometimes HF was combined with pyridine. HF pyridine is a good reagent. HF triethylamine is a good reagent to cleave the silicon containing protecting group. Simple ammonium fluoride NH4HF, ammonium bifluoride was used. Potassium fluoride sometimes was used, but potassium fluoride is very much hygroscopic, it is very difficult to handle. So, potassium fluoride normally is not used, but you can use this all these compounds. TBAP was the most widely used compound to cleave any silicon containing oxygen silicon bonds or carbon silicon bonds. HF pyridine also was used, HF triethylamine, ammonium fluoride, ammonium hydrogen fluoride, all are used. So, probably this set of reagents we will be using when you talk about protecting groups in detail. So, okay, we will just continue our discussion in the next week. Till then, goodbye, have a good time.